Hello and welcome to this clip on how to analyse your proton NMR spectrum. There's quite a lot it's assuming, so the screen is quite clear about that. It's assumed that you're familiar with carbon-13 NMR and the basic theory behind nuclear magnetic resonance. In addition, you need to be comfortable with splitting patterns and the n+1 rule, integration ratios, and the use of deuterated solvents and D2O. So let's do a very quick roundup of the things that your analysis should contain. I've listed them down the left hand side, so we'll go through what each of them actually tells you. So the chemical shift value gives the general hydrogen environment as found on the data sheet. And to do this, what you do is cross-reference the location of the peak on your spectrum to the data sheet. This gives the number of non-equivalent hydrogens in the adjacent environment to the one that the peak comes from. And what you do is use the n+1 rule. So therefore a singlet means that there's no hydrogens in the adjacent environment because 0 plus 1 makes 1. A doublet means there's one hydrogen in the adjacent environment because 1 plus 1 makes 2. A triplet means that there are 2 hydrogens in the adjacent environment. 2 plus 1 makes 3. Quartet means that there are 3 hydrogens in the adjacent environment. 3 plus 1 makes 4. So the relative peak areas may or may not be provided in the question, but if they are, you need to do something with them. What they tell you is the number of hydrogens in the actual environment you're looking at. So the final part is perhaps the most difficult part. You look at the general environments that you've located using your data sheet and then apply these across to your molecule. You'll have some information about it and you'll be able to try and deduce what they might be. By this stage you'll have already got a few marks, so don't worry if you get to this point and get stuck. Okay, so let's have a look at the data sheet just to remind ourselves what part of it we're going to be using. So don't forget, if you're doing a hydrogen NMR question, it's actually the bottom one, not the top one. The top one is for carbon. So I know it might sound obvious to sit there listening to me saying this to you, but you'd be amazed how many people make the mistake. I've done it myself. It's easy just to not check. And if you look closely, the scales themselves, the chemical shift scales, actually are significantly different as well. So that might be a clue too. Okay, so let's now look at how we might approach this in terms of laying out the information. So let's have a quick review of some of the proton NMR ideas we've been covering. So the splitting pattern tells us how many protons are in the adjacent environment. So let's say we take the CH3 on the left-hand side. So we have 3 protons in that environment, as you can see. But in the adjacent environment, there are 2 protons. So what this means is you get a splitting pattern of a triplet. So a triplet comes from that CH3 as the n+1 rule is applied to the 2 hydrogens next door. But if we were to take those 2 hydrogens in that CH2 group and call that our environment, the adjacent environment is the CH3. So this time there are 3 hydrogens next door, so you get a quartet as our splitting pattern. But on the CH3 group next to the ester functional group, there are no hydrogens on the adjacent environment, so this time a singlet is applied. So the adjacent environment would obviously be the oxygen atom that I've highlighted in grey. So the integration ratio tells us how many protons are in the actual environment we're looking at. So it's a 3 to 2 to 3 ratio with the protons in the 3 different environments we've just looked at. So D2O, if you remember, is used to eliminate from the spectrum the presence of OH and NH groups. Because what happens is the peaks disappear if the sample is run a second time with a deuterated solvent. So remembering that deuterium, being an isotope of hydrogen, has an extra neutron in its nucleus, so it's got 2 nucleons instead of 1. So it's an even number. So hence no spin and therefore no NMR signal. So when many people are in an exam setting, under pressure perhaps, and quite often with the question at the end of the exam maybe, they revert to analysing a spectrum using lots of text in their writing. So they're trying to include as much key information as possible, which is the right thing to do. My advice would be don't use text. Why do I say this? Because you can very easily end up getting confused because you're repeating yourself. So how do you do this instead? I'd recommend using a table to lay your data out. Not only does it help you organise your thinking logically, but the examiner will also appreciate the clarity in your answer when marking your paper. So let's think about how to do this. So let's look at a spectrum. So we're not told what this particular compound is. All we're given is this information. Now on the graphic there's obviously a little bit of information to help you along the way because we're introducing this idea. But what I suggest you do is you split your table into these columns. And if the spectrum hasn't actually labelled the peaks, like in this one, I suggest you do it yourself on the spectrum you're given. So I've now added the information from the data sheet or graphic that is similar to it, and what we do is we take the peak A and we look for the chemical shift value. So the chemical shift value is around 3.6. So let's assume for the sake of argument we're told that the molecule is C4H8O2. We can now select environment. So we're going to go for OCH. I'm going to underline the H because it's that particular environment, that particular atom, that hydrogen, that's giving us this peak. So looking at peak A, we can see that the splitting pattern is a singlet, which obviously means the number of adjacent protons is 0. Now the next one, which is peak area, it depends on whether they give you information about the peak area in the actual spectrum. In this particular spectrum, the graphic that I've used didn't give you any information about the peak area, so you can't really say what the area is under the peak. What this bit represents is the number of hydrogens in this actual environment as opposed to the number of hydrogens in the adjacent environment. So what I'm going to do is I'm going to add something to this so we can put the peak area in. I'm actually going to not improve the graphic, but just put something else in. So if we assume the question provided this information, have a number printed next to the actual peak, or somehow they would tell you what the number of hydrogens would be. So normally they print a number next to the peak. So assume they've done that. We can now put in the rest of that row, because the peak area represents the number of hydrogens that are present, which now means we can say it's not just OCH, we can say it's OCH3. Let's do peak B now. So we can see now that we're looking at an environment with a parts per million or a chemical shift between 2 and 3. It's approximately 2.3. So I'm going to go for OCCH. If you can look up in the top right hand corner of the screen, you can see it's the second environment down in the selection we have. So using the peak area I'm given, which is 2, that means that there is a number of hydrogens in that particular environment is 2. The splitting pattern is a quartet, so using the n+1 rule, that means there's 3 adjacent hydrogens. So that gives me 2 things. That gives me CH3, CH2, C double bond O. So pause the clip now and see if you can do peak C. So the thing to do is to work your way along methodically using the data sheet and see how much you can piece together now. So hopefully you got something along those lines. It's a triplet, so there's 2 adjacent H's. It's in the RCH part of the chemical shift spectrum. Peak area 3, so number of hydrogens in that environment is 3, so it's CH3, CH2. So putting all this together, we can now put a structure in. So that means our compound is methyl propanoate. So a chemist isolates compound H from a mixture and sends it for an analysis. And the initial analysis shows the molecular form of H is C10H12O. So it gives you a typical spectrum. This one's a bit more complicated perhaps than the one we looked at a few moments ago. And bring it down. It says in the NMR spectrum the peak at 3.7 parts per million would normally be expected a chemical shift value about 1 part per million to the right. i.e. at 2.7. So let's try and collect our information. So first of all, let's label that up so we can remember that for future reference. So going back to the first part of the question, we also have some information about the molecule itself. So we've got a molecular formula and we've got the number of carbon environments. So what we need to do now is clear some space to do our table like we talked about earlier. So we can put in our headings like that. So my next move is to label up my peaks A, B, C, D and E so I can work clearly from left to right. So now what we need to do is put in the information that is easy to do. So that's the chemical shift value, the peak areas, because they tell it to us, and the number of hydrogens that actually produces or refers to. So while we're doing this, let's have a look at some easy marks. The peak area is the number of hydrogens in that environment, and the chemical shift values, they give environments that can be used to make the conclusion. So it's worth pointing out that just the environment as printed on the data sheet won't get any marks so far, as you have to deduce something from it. So to get something from it, you now have to think about C10H12O, 8 carbon environments. How do I piece this all together? So let's start with the aromatic rings, because they account for 6 out of the 10 carbons. So we know we've got 6 carbons because it's an aromatic ring environment, and there are 4 hydrogens in that environment, so it must be C6H4. That means there are 2 places on the benzene ring left for something else apart from hydrogen. So the next aromatic environment, it suggests CH2CH3 because there's 2 hydrogens in that environment, but there's 3 hydrogens in the adjacent environment, because I'm using the number of hydrogens and the adjacent hydrogens. So that gives us CH2CH3, so we already have part of our structure. So I'm going to create some space here, so I'm going to get rid of the easy marks section because we've covered what that means already. So going to peak A, I can now say it's CH2CHO, so the aldehyde group COH, C double bond O with an H attached to the carbon, has 2 adjacent hydrogens because my splitting pattern says a triplet, so I can put CH2CHO in. So my next peak is at 3.7, which should be normally at 2.7. And we know that the peak area is 2, so the number of hydrogens in it is 2. And we know also that the adjacent number of hydrogens is 1 because it's a doublet, so it's CH2CHO. So the final part of the puzzle is to work out what the HCr means. So this must be our CH2CH3. So we still have to put a structure together, but we've gathered about 3/4 to 80% of the marks already just by doing this analysis. So it saves us having to work out lots and lots of text, lots and lots of writing, where we might end up getting confused between one peak and another. So let's now try our structure. We know we've got a benzene ring, and we know we've got that structure because that's what one of our peaks tells us. But the problem is, where do we put the CH2CH3? There's all these different positions you have to put it on. This is where the 8 carbon environments come in. So we've got 3 there already, and we've also got a CH2CH3 to put in somewhere. CH2CH3 gives us another 2 carbon environments. So if we put that opposite the situation, the position of the aldehyde group, now we can start putting in the other carbon environments, labelling them up. So you can see that using the fact that there are 8 carbon environments, we can deduce where to put the 2 substituents on the benzene ring relative to each other. So it's a 1,4 substituent. So that was quite a challenging one, I'd say. That total there is 9 marks. So I hope you found it a useful sort of introduction on how to do the analyses for NMR in a little sort of more straightforward way, perhaps in a way that might be easier to start picking up the marks. So about 70% of the marks roughly, like I said, would be from the table, and about 30% of the marks would be from the structure. And even if you didn't get the structure entirely right, if you got the 2 positions, perhaps you got them wrong, you'd still get some of the marks. It's actually quite easy to pick up a significant proportion of the marks. So the 2 bits of advice I might pass on would be, First of all, it's quite easy to start picking up marks quickly, so please don't give up even though it might look like it's quite hard. Definitely practice tabulating your information, so it's worth going away and trying some examples out and seeing if you can put a table like this down. When you get lots and lots of space given to you, your first instinct, I know, is to try and write out as much as you can before you forget an idea that comes to you. Try to keep calm, count to 10, and write the table out and see what you can fill it with. You never know how many marks you can pick up. Okay, so thanks for listening. Hopefully this was fairly useful, and maybe see you soon.